Alright, if you recall, we were discussing about the change in the density with respect to change in the temperature and things like that. I want to go back to the basic model what we started with, trying to understand the system. Okay. See, we have so far what we have done is we have talked about the sources, okay, different kind of sources, the line sources, the point sources, the industrial sources, the domestic cooking, all kind of sources we have talked about. So sources we have talked about, and even we have talked about how to find out how big is a source, and that we did through emission inventory. Okay. So not only the source types, but also the power of the source or strength of the source, that we have done so far. So you have a very good idea. Suppose if I ask you, please find out what are the sources in Kanpur. You can do the exercise, and I also tell you, well, find out which are the larger sources like the power plants or the industry or a fertilizer plant. You can do that one. If I ask you, okay, go and find out what are the vehicular pollution sources, that also you can do. Not only you can identify them, you can also quantify them as to how much is the emission, and that is very important when we talk about this system. And you recall, we also talked about the receptors, especially about the health point of view, how the people are affected. Air pollution and health. Okay. To connect these two, we need to understand the transport of the pollutant. And if you recall, we said transport of the pollutants in the air, that study we call as a meteorology. Okay. So our focus in coming lectures will be on the transport that is governed by the In meteorology, we talk about the two things. Okay. The movement of the pollutants, that can be through the two means. One is a vertical movement, another is a horizontal movement. And so when we talk about the movement of pollutants, horizontal and then the vertical. Horizontal, again we have talked briefly through the wind roses, if you call, wind speed, the wind direction. But the focus now in this lecture and the coming lecture, how the vertical thing will be decided, how the vertical movement of the pollutants will be decided, how high they will go, how much they will disperse vertically, because that is also very, very important to us. So now if we are focused on the vertical movement of the air pollutants, then we say, all right, if the vertical movement is important, then what is that causes a vertical movement? Okay, vertical movement is largely caused because of, as we go up, change in the density. Okay. Okay, as we go up, the change in the density, and change in the density, it comes about because of change in temperature. Okay. So we want to see how the temperature changes as we go up vertically, because that's largely going to decide about the vertical movement of my pollutants. Things go out from the chimney, you have seen the pollutants, sometimes you have seen the chimney pollutants just vertically continue to go high and high. Sometimes they just come down, sometimes they are dancing like a, we call it dancing plume, and sometimes you see very thin plume traveling kilometers and kilometers and things like that. That vertical movement is decided by change in the density and change in the temperature. So our focus will be to see how the temperature changes as we go up. And generally we all know the temperature decreases as we go up. Shimla is always cooler than Delhi. Mount Everest will be more cooler than what we have here. So that we understand that there is a change in the temperature decreases as we go up, especially in the troposphere. Okay, so we want to look at the physics of the things, how they change. Okay, so so we'll try to see this one, but for doing that one, let's take an example. Okay, I take a small parcel of air which is here. Okay, and suppose I've given it vertical push and the temperature is higher. So as you see, as it goes up, the particle or the parcel of the air becomes bigger and bigger. And something like this. Okay. So the vertical movement you see here is changing. Because the density decreases, okay, the pressure is decreasing, as a result there is an expansion in the size of the same parcel, same mass, but you see as we go up it changes. So that is what is one thing we have to understand, the pollutants can change like this. And so what is happening, I can say here, there are two things happening. Volume expansion okay, and what else? The volume is expanding and change in the temperature of the air parcel. Okay, surrounding temperature, whatever it is, that is not being affected because of this one. And then you say volume expansion and change in temperature. Okay. Suppose make an assumption here that, well, because of the change in the pressure, as things are moving up, expansion is taking place, but there is no transfer of heat between the parcel of the air that I am considering to its surrounding, okay, which is a reasonable assumption. Things are happening so fast that the temperature transfer or the heat transfer between the air of the particle, air of the air parcel that I am considering with the air surrounding this one. So if you agree with that one, there is no transfer of the heat between the parcel of the air as it is moving up with the surrounding air. What such process is called? Adiabatic process. So assumption, I am trying to remember, we are trying to address this thing, how the vertical movement of the pollutants will take place, and that will be decided by as it moves up, what will be change in the temperature. So here the assumption, which you all agree, reasonable assumption, it may have some implications, but the process I can define this as the adiabatic process. So we say no change in heat input or output. So the process which we will consider and use that one to address our issue, we call this process, or we assume this one is an adiabatic process. Okay, so this is the two things that will happen, and that these two things we want to define them with respect to considering the process to be adiabatic. And so this is our, if you like, I will put here, this is our assumption. Okay, same thing. Okay, I want to give you the different examples so that you have the little feeling as to what really happens. You all must have seen the hot air balloon. Okay, hot air balloon is something, what you can see, the hot air balloon is starting from here and it goes up. And you know the record that has been made by the Indian for flying the highest altitude, who was the person? Vijay Mallya. This thing, Vijayapati Singhania. He made the record of flying very high with the hot air balloon. So if I try to make a little thing to give you a little more clarity on the hot air balloon is, let's see, let's draw the picture anyway. Okay. It might look, generally it is very colorful as you will see. Okay. And then you have generally two persons sitting here, blowing the hot air through this thing, and it goes up. So suppose you are traveling up with your friend and it moves up and things like that. What you will notice is that as you move up, these are the strings, okay? These are the strings. As you move up, this portion which is part of the balloon, it tends to bulge out. It becomes bigger and bigger and bigger and bigger. So you have to be, not only this is strong, then you will see after some time these things are fixed, but this portion which is a kind of balloon, it bulges out. So same thing, as it is going up, it comes out bigger and bigger and bigger and bigger. Maybe you don't notice it because it is going high up in the air. So same thing, the very same phenomena is happening. Here you are moving continuously up. We had the same parcel, same mass, and you see the volume is going up. So what we'll do is that we'll try to with the help of the physics, okay, and laws of thermodynamics. I'll go a little fast because this is all you've done in your high school and things like that. So what I can say here is change in internal energy and the work done. So that you want to represent as du plus dw. Okay, let's say this is equation number 1. I'm not writing, but you can write from the laws of thermodynamics. This is basic equation we have been doing, over the years and years. This one you can write this as Cv dt plus Pdv. This is your equation number 2. Okay. I can also write for the unit mass of the air or gases that I am talking about, for the unit mass. Let's say that is my equation number 3. Okay. If I differentiate this equation, okay, I can write this as Pdv plus Vdp. R and Ma are the constant. So R dt by Ma. Let's write small a. So that is my equation number 4. Okay. I want to go back to the equation 2, and I can very coolly put dq equals to adiabatic process. What is dq? 0. Fine. So I can put dq equal to 0, and then therefore the Cv dt, putting dq equals to 0. So Cdv will be equal to minus Pdv, and if you like minus Pdv, if I take up the minus Pdv, Cv will be equal to minus Pdv, and I can pick up minus Pdv from here. That will be what? Cv dt, and then I can, so this is my Cv dt equal to minus Pdv. Let's go basic with one step, one time. And in place of Pdv, I can write like this. So this will be equal to R dt Ma, okay, minus, should I put minus here? Okay, and then plus V dP. Okay. So now what you see here with this expression, I can, well, I'll save some time, I can write an expression how the change in the temperature with dP. Can you write that quickly? See, you have the dt term here, bring this one here, okay, take the dt out, and you can write the expression for dt by dP, and that expression comes out to be, or if you want to quickly say, want to write that expression and see if it matches with me. Go ahead. V upon okay, whatever that you come up with. Okay, let's do this one. V upon CV plus R by MA. Anything else? All agree to this thing? Okay. Let's put this on. Okay. I again use my sum relationship here, and I can still place the value of V from here. In this V, okay, let's give it number if you like. This is 5, this is 6, this is 7. Putting the value of V in 7 from 3, okay, putting the value of V from which equation? Or basic equation 3 in, where do I want to put? In 7. And then I'll get some expression which is of interest to me, and that expression again dt by dP, that expression again I would like you to give me and see if that matches. R by MA whole upon this into T by P. All right. Well, finally we'll write it in a little different way, but whatever you're getting, let's put right this way. T by P and whole thing 1 by, okay, CV plus R by what? MA. Great. Well, you get the same expression as I get. Okay. So we'll remember this equation. Don't forget this equation, because this tells me how the temperature will change with respect to pressure. So let's write this equation as 8. Okay. No problem. You have derived that one out. Okay. Suppose now I want to invoke the equation of hydrostatic equation. Okay. So we say recall hydrostatic equation, and I am writing for the atmosphere. So what I can say is Z is my vertical direction. Okay, Z is my vertical direction. Is, you agree, or I need to do something else? Minus sign. Okay, minus sign. Okay. And this again, what I can do is for this the rho thing, again I can invoke my universal gas law, which you see in equation 3, and I can put the value of rho in this one. right? Okay. So do that one. So we say dP by dz, and then again you give me the expression, take rho in the form of mass by volume from your equation number 3, okay, and give me the final answer as to what you get. So I can put the negative sign very conveniently. What is that you are getting? P G is there anyway by RT. Should be M term should be also be there. Don't forget there is a MA here, so that will come in the unit mass is here. This M here, so this M, don't forget what is this? This is not unit mass. This is the molecular weight of the gas which we are talking about. So this is not unit. So this M, because this has to be mole fraction, so this M we took that as 1. So that is equal. We may even write it a little bigger. Doesn't matter. So what else will come here? MA up. Does everyone get that? And the G, of course. And let's write this equation as 9. Okay, very good. So what I can do now, the life is simple. I got two equations that I derived. That is equation number 8 and equation number 9. And recall all the things which we are doing this one for, to find out how the temperature changes as we go up. Okay, we know qualitatively that it changes, it reduces as we go up. Okay, so but then what I can do, I can get the expression if I multiply equation 8 with equation 9. Okay, so on multiplying 8 and 9, you should get some expression which should look like dt by dz or something. Okay, so that expression, please give me that expression, whatever that comes out to be. There will be some cancellation here and there, and let's see what you get up with.
G upon CV.
Okay, G upon CV plus R by MA. This I can put in the bracket if you like, and negative sign, right? Okay. If that is the case, if you agree with this one, this can also be written as and where the Cp hat, specific heat at constant pressure for unit mass, or specific heat capacity. Or should we say specific heat capacity at constant pressure. Complete the sentence, constant pressure for unit mass. Okay. Okay, excellent. Great relationship, and we are going to use it consistently many times in coming lectures, and this is a very important thing we came up with. And this one, let's use the other side. Okay, so if you put the constants of G and Cp hat, which I am not putting the numbers as such, but finally giving the answer, it's better to make this as approximately as approximately. Okay. This is what is that. This is thing which we call this as the. This one we call as the terminology which we use in the air pollution. We call it lapse rate, because there is a lapse in the temperature. So, or exactly we call it adiabatic, because we have invoked the concept of adiabatic lapse rate. Okay. And generally what the value of Cp that we have taken in here is, see, the moisture content is such a thing which is very much variable in the atmosphere, right. So what we have done here, we have, while putting the value of Cp, I have taken the mass of the air and all air as dry. So if you don't mind, I'll put the word dry there and call it dry adiabatic lapse rate. Okay, and that is equal to minus G over Cp, and that's equal to 1 degree centigrade per. Never ever make a mistake of calling this as the, that is a big, that's a big sigma. What do you call that? Gamma, yes, big gamma. So big gamma, what you see here is a big gamma equals to, it already account for the negative sign. Never write the big gamma equals to minus 1 degree Celsius per minute. You will make mistakes. So that point I want to make it again clear and clear to you. This minus sign is already taken in, okay, when you are talking about the lapse rate, because your word using the lapse rate. So the lapse rate is this thing. Okay, that is very, very important thing which we came up with. Okay, and let me also tell you, this derivation what we have done, we simply use this laws of science and physics. This will be also be valid whether you are on Mars or Venus. So there also you have the atmosphere. But what will be the different? The G will be different, the Cp will be different, and Cp will be determined by the composition of the atmosphere, because in Cp you have not only you have the heat capacity which will depend on to the various gases that are present. So molecular weight also will change, but the derivation so far what we have done, okay, it holds good whether you are onto Earth or you are on Mars or you are in Venus. Okay, the things will change, and this is what we have got as very, very important thing, and that's what we will be using in the next time. So now in a way this answers you that why is the, and not only why, but how much the Shimla will be cooler, what will be the temperature at the Mount Everest, and things like that. Okay. But again, having said all these things, okay, the actual life or the real life, okay, real life, this situation which is more like a little bit hypothetical, adiabatic condition, and moreover the more problematic more than adiabatic is that we have considered to be dry. Atmosphere is never dry. Okay, so the real life, okay, real life atmosphere is seldom adiabatic, or especially the range what interests us, like up to like from here to 2000 meters or so, is seldom okay. So in that case the atmospheric lapse rate, okay. So here let's write this right as VALR, okay, and then this in real life atmosphere is seldom adiabatic. So the atmospheric lapse rate, okay, this atmospheric lapse rate will be little different than what we have derived. Okay, so this atmospheric lapse rate we call that as the environmental lapse rate. Okay, the real atmospheric lapse rate. Real means actual at the time whenever you are considering the time. This we call as or ELR. Okay. Why we are using the word ELR? It's just simply to avoid the confusion with the word adiabatic, because I could also use the word atmosphere here. So never be confused again, because in the books and things like that they will use the word ALR, and ALR is not atmospheric lapse rate. A stands for adiabatic, because the confusion comes so easily. So to avoid the confusion, many books and we will use the word when we want to define the real environment as the environmental lapse rate. Okay, and ALR will not refer to atmospheric lapse rate but adiabatic lapse rate in the atmosphere. Okay. Okay. So we simply one time I just want to show and plot this to you. Okay. Now we'll have the many graphs in this lecture and many lectures, which will standard thing we'll put here, height above the surface level, and we'll talk about the temperature here, because that is what is of great interest to us, the relationship between T and Z. Okay. So we're talking about troposphere. How much is troposphere? How far I can go? How much? 16 kilometer. Of course, at the poles it will be different, and the equator it will be different. At the poles it will be less, but let's say generally, let's say it just goes up to the 16 kilometer. Well, I break too many chalks. So normal temperature you can start with whatever 28, 30 degrees, doesn't matter. Okay, and it may reduce a lot. I mean, I will not be able to give you the exact number here, but then you see here, it will reduce here like this. So this is your adiabatic lapse rate. What do you expect? Okay, this is what I can call this as DALR. Okay. Suppose some percent of moisture is there, okay, then what will happen? I will still have the lapse rate or temperature decreasing will be on this side or this side. This side or this side? The left side? The change in the temperature will be like the heat capacity of that thing will be more, right? So Cp will be smaller. Okay, so you may get something like this, depending on the moisture content. So in a way, now if I want to talk about, so we'll remember these things as to the lapse rate business, and that we'll use it several times. So since we have the time, so we'll do what we do is plot few things. Okay, same Z here and T here. Okay. So what I'll do is the DALR, as a matter of convention, I'll always write or always draw that as a dotted line rather dashed lines. So moment you see here, when I'm making this thing, is always, whenever you see a dashed line, it means we are talking about this is what the situation. And suppose I went and really measured the temperature with respect to height in the atmosphere, and I got a temperature profile, and this, what you see here, the solid line is the actual thing. Okay, this is what? Okay, so no confusion, DALR and ELR. ELR is my actual, and I like to call it the environmental lapse rate. Okay, So what you say here in this picture is such a situation, okay, we call that as neutral atmosphere, okay, because atmosphere is behaving the way the adiabatic lapse rate will behave.
So ELR must always be right of DLR.
See that this thing is hypothetical in the sense this I can plot here or here or here. So whatever temperature I started with, the way the temperature will decrease. This is standard line. This I can draw here or draw here. It doesn't matter. Or does it matter? I mean, it matters as to if you want to find out the temperature, but this is just our, in a view, this is our reference thing. Okay, where we are with respect to the reference thing. So this is just a reference. Okay, and of course, but you don't want to plot it somewhere here or there. So this is my reference, and I want to see with respect to the reference how my atmosphere is behaving, okay, what my atmosphere is doing. Okay, that's what the idea is. So one situation can be, then this is what is this thing. So it is behaving exactly the way the adiabatic lapse rate is. Such atmosphere, I'll explain you what is meaning of this one. Such atmosphere, we call this atmosphere is neutral. Okay. Situation number 2. Z and T. This situation can also come. So standard conditions or the reference conditions as this one. Okay. And then you see here the temperature, in fact, instead of decreasing, suppose it increase. Okay. So what you can say, here it was, here what was the DLR was equal to whatever 1 degree per this was like what, 1 degree per 100 meters change in the temperature. Okay, this one is, okay, let's say well, there is no change. Of course I can also represent this, there is no change. So there is no change. Okay, or to make the things a little more interesting, I can even increase this one, which is not uncommon kind of thing. I can increase it. Okay, and suppose after the increasing, I'm calling that. So this was my this thing, and this is my this, and this I'm calling this as, let's say, 0.5. Okay. Do I need to put some sign here? What sign I put? Negative. Because this temperature is increasing. Okay, it was decreasing that I have taken for this one. So this is the thing. So what you see here, DALR is greater than ELR. Agree? You agree or you don't agree? We agree, right? Because there is a negative sign there. So if that is the situation, we call the atmosphere to be stable or unstable? Stable or unstable, that you have to, unstable. Atmosphere is called stable. Okay. Okay. Well, we'll explain. We'll say why it is stable. Third situation which can be there is the temperature is decreasing rather rapidly. Okay, so this is my DLR DLR. So what I can say, correct, and the atmosphere is unstable. Okay. Here why we are calling it stable? Okay. Just see, suppose I have a beaker full of water. And what is the situation? My temperature, and this is my height of the beaker. Okay. What is happening here? At higher height, I have the temperature which is higher. Okay. The temperature is lower here, right? In the beaker, suppose I take a big beaker, and then I am drawing the profile of the temperature with the temperature profile with respect to height of the beaker is, let's say, like this. It means as I am going up, the temperature is increasing. So in a way, what I am doing, I am heating the beaker as if from here. I put a burner here and I am heating it here. You agree with me? Then only I can have the high temperature here and the lower temperature here. See, if this is what is the situation, you are heating the water from the top to get a temperature profile which looks like this. What will be the atmosphere? What will be the water doing? Will it be boiling or jumping, or it will be quiet? It will be quiet because there is no convection, nothing going up and down, and there is no turbulence and things like that. So water will be more or less sitting very quietly as a stable water. Okay. And same thing in the atmosphere. This I gave you the example, but same thing if you look at the atmosphere, in a way the atmosphere in some sense, how it is done, that is a different thing. And in that sense it is being heated up from the top and temperature is lower at the bottom. So as a result there will be no convections, there will be no current, there will be no turbulence, there will be no mixing, and as a result things will, what we will call that as a stable. Water is sitting stable. So the atmosphere is also sitting stable, so it means pollutants will not travel or will not jump or will not do the things what they do. Okay. But here, if you look at the same thing here, what I am doing here is, okay, is that let's make the beaker business here again. And I am heating from bottom. This is my burner. Okay. So obviously temperature will be higher here, temperature will be lower here, and so I will get a profile something like this. Okay. And then you will see there will be convections, there will be turbulence and things going up and down, and that is what that's why we call this as this atmosphere as unstable. Just things will be unstable, and probably when I am not heating it altogether, then the atmosphere you can call that as the neutral atmosphere, and then this thing. And then all these three conditions in the atmosphere are common. See here, atmosphere can behave like this, atmosphere can behave like this, and atmosphere can behave like this. So when you can imagine with respect to what is happening in the beaker, exactly the same thing happens in the atmosphere. So you can almost say when suppose if I ask you, the plume is dancing, going up and down, and there is huge turbulence, where are the situation? Your situation there. Okay. When I say, well, the plume is just not moving, it's just like a trickle, small thing which is traveling, this situation is like this. It means there is no turbulence at all, things just tend to move, there is no vertical movement, especially our lecture is focused on the vertical movement of the pollutants. And then you see here, there will be reasonable movement, that kind of thing. And that is what, with respect to these things, we can define the behavior of the atmosphere. Okay. I think I will stop here, and unless there are questions, we can take some question, and then we will slightly get more into little more specification within these things. Because if it is here or here or here, we have done the broad picture, and we'll see, we'll get into little finer things of this one in the next lecture.